about 350 years ago, Isaac Newton attempted to answer why objects released from a height fall down rather than up. Newton postulated that some kind of a force was attracting the object to the Earth. Analyzing the motion of the planets and satellites, Newton began to realize that he had stumbled onto a major discovery, the phenomenon that held the entire universe together. Every object in the universe, no matter how small or how big, attracts every other object with a force which is directly proportional to its mass and inversely proportional to the distance between the object and other objects. Mathematically, F is equal to G large M small m divided by the square of R. This is the universal law of gravitation in mathematical form. It is universal because the value of the constant G remains the same everywhere in the universe. It is independent of the shape or size of the object. The value of G can be calculated by modifying the above equation. G is equal to F multiplied by the square of R divided by the product of the masses. The required values of F, M, small m and R being put into the equation gives us a value of 6.673 multiplied by 10 to the power negative 11 newtons square meter per kilogram squared. What is the significance of the universal law? Number 1, it holds us to the earth. Number 2, it determines the motion of the earth around the sun and the moon around the earth. Number 3, on the scale of the universe, it provides the structure to galaxies and galactic clusters. Motion under gravitational influence, also known as free fall. When we throw a stone upwards, we observe that it loses speed as it goes higher and higher until it reaches zero velocity. Then it starts to accelerate in the downward direction. This motion is purely determined by the gravitational force acting on the stone. For simplicity, we do not consider the role of air friction at this stage. Such motion is called free fall. It is important to note that while we do use the word fall in free fall, the term refers to both the upward and downward motion of the stone, as free fall implies only that the path of the stone is controlled purely by the gravitational properties of the earth and the stone. Another salient fact to point out is that the acceleration is acting on the stone constantly, even when it is resting in our hand. Let us figure out how to express this acceleration in numerical terms. As we know, the force due to gravity on the stone is equal to the mass of the stone multiplied by acceleration due to gravity, or F is equal to mass multiplied by small g. It follows that small g would be equal to F divided by the mass of the object. Substituting the formula for the universal law of gravitation in place of F, we have small g is equal to capital G times large M divided by R to the power 2. For the earth, this value is 9.8 meters per second squared at the surface. We have assumed that the earth is a perfect sphere. However, in truth, the spin of the earth causes the earth to be slightly bulging at the equator and slightly flattened at the poles. This means that small g at the poles is slightly greater compared to the equator. The mathematics of free fall in the previous chapter, we determined 3 equations of motion in one dimension. Here we will make the following assumptions. The object moves only under the force of gravity, which means that acceleration is equal to small g at all times. Second, the object is confined in its motion to the vertical axis. And for mathematical clarity, g is considered to be negative when the object is traveling in the opposite direction to the acceleration. G is considered positive if the object is traveling in the same direction as the acceleration. Based on the above assumptions, we may modify the three equations of motion by substituting S, which is displacement, with H, which is vertical displacement, and A, which is acceleration, with small g, which is acceleration due to gravity. Let us summarize what we have learned so far.